All right. So good afternoon, everyone. I hope you're all doing great. I'm happy to be the SLC moderator for today's Friedman Family Lecture hosted by EERI chapter at University of Nevada, Reno. I'm Ahmed Hassan. I'm a PhD candidate in the structures group at UC Davis. It's my pleasure today to introduce Dr. Troy Morgan. Troy is a principal engineer with Exponent in New York. He received his bachelor, master's, and PhD degrees from UC Berkeley. And he is registered as a professional engineer in 6 states, specializing in the performance-based analysis, design, and assessment of structures under extreme loadings. He's also served as a consultant on major projects, and he has like a substantial consulting experience with the nuclear power generating industry and seismic risk evaluation for new and existing structures. And in today's lecture, Troy plans to talk about risk assessment and seismic risk mitigation in the engineering practice, walking us, as shown in the title, through some adventures in risk mitigation and seismic risk mitigation. We will have like Q&A sessions, right after the talk. And like if you have any question during the lecture, maybe you can type it in the chat and we can compile it at the end. And feel free to stay after that for like a more informal career and professional development talk with Troy. Without like any further ado, I will hand it to Troy. Yeah, thank you.
Okay, great. Well, thank you for the introduction. As you said, this talk really is about kind of a sampling of different projects I've worked on in the area of seismic risk mitigation broadly. And the idea is to draw on some of these projects and point out what lessons that we can learn from them, kind of maybe where the profession is heading in some cases. And then I'm also going to talk a little bit at the end about a project that we're working on at Exponent involving risk analysis of electrical assets to wind hazard, which doesn't sound like it's earthquake engineering at all, and it's not. But a lot of the work we're doing it with utilities is really basically transforming a lot of the pure methodology that was designed and developed for earthquake, performance-based earthquake engineering, and really using it more broadly for wind hazards and electric utilities and other things like that. So it's really, a lot of ideas are born in the world of earthquake engineering and seismic design, but that have really found applications a lot more broadly than that. And I think that's something that we should be excited about, and we should be proud that the tools we've worked on for all these years are making their way to other other disciplines and solving other important problems as well, in addition to that of the earthquake. So, I'm going to start by talking a little bit about EERI. EERI is an organization I've been involved with since I was a graduate student. I was the president of the student chapter at UC Berkeley, and my distinctions in that role were by the chapter not completely disbanding and going on for an additional year after that. I can't say we were the most active chapter, but we were a chapter nonetheless. But my exposure to EERI started there, and really going to the annual meetings and participating in committee work has really been some of the most rewarding parts of my career. I've met lifelong friends and colleagues through the organization, and I'm proud to be an active member. And EERI is unique because it's one of the few organizations in the field that really spans not only technical disciplines like geotechnical engineering, structural engineering, but also public policy, some of the pure sciences, geology and seismology, and even things like emergency response, involving the healthcare professionals. So it's a broad organization, and it's really an opportunity to learn a lot about kind of the field outside of our discipline, where we tend to get a little bit maybe hyper-focused at times. And really the mission of EERI is kind of straightforward, not easy, but straightforward, and it's really to advance the science and practice of earthquake engineering, improve the world in the context of seismic hazard mitigation, and really improving people's quality of life worldwide. Something we do as well is educating the public. And I show this slide to highlight the fact that I've had a side career of going on TV shows that no one has ever or will ever see, which has been very exciting. So it gives me a chance to really embarrass myself in a way that no one will ever will ever find out about. But here I am telling you about it as well. But it's the point is not that, it's that EERI is one of the mission of EERI is to, in a public setting, educate you know, people, whether they're stakeholders, homeowners, whomever, and really inform them as to earthquake risk, what it's about, how it impacts their lives, and really gain some I think exposure and policies around seismic hazard mitigation will not move forward without buy-in from a substantial number of stakeholders, and without an organization like EERI to really kind of promote that. There's really it's hard to get any traction, especially in terms of lawmaking and other things like that. And then I think the Learning from Earthquakes program is one of kind of a unique aspect of EERI that I personally have benefited from. I've been on 2 earthquake reconnaissance missions in Christchurch, New Zealand, which I'll mention today, and then in northeastern Japan after the Great Tohoku earthquake, both in 2011, coincidentally. And so this is something that students and professionals can get involved in. We actually, at the last annual meeting, we had a huge funding drive, and we got a huge chunk of funding for the LFE program. So it should be going forward for years to come. And really the idea is what it sounds like. It's to learn lessons from earthquakes that happen around the world, and be able to take those lessons and really improve our practices, and maybe not make the same mistakes twice in a way. And then there's a lot of benefits for students. So I definitely encourage students to join. The membership dues for students are, I don't have the number off the top of my head, but I remember it being a very small fraction of what it would cost once you're out of school. And there's a great, there's travel grants to go to meetings. There's competitions at the EERI annual meeting, including the seismic design competition, student paper competitions, which I know Maha is a member of the Student Awards Committee, which I'm taking over as the chair of that committee this year. So if anyone needs to Venmo or send me any cash on the side, we'll be sure and put your application right up front. And then the journal EERI Spectra is, I think it's the highest quality journal that's devoted to earthquake risk and hazard mitigation, and really the study of the field. It's like I said, like EERI, it's very broad. It encompasses all sorts of topics, from public policy to seismology to engineering. It's very high quality, peer reviewed by experts in the field, and so it's that alone would probably be worth it for membership. So take a look at EERI, go to the website, and certainly consider joining if you haven't already. It's really worth it. And I'm not just saying that because they're funding this visit of mine, but I have been a member since the earliest time I can remember, and nothing but positive things to say about it. All right, well, I'm going to transition from that rather seamlessly into some of the substantive matter of my talk, which is to get into kind of one of the first projects I want to go over. And it's a project I worked on fairly early in my career at Exponent, and it's really got some fascinating components to it. And so I want to use it as an opportunity to highlight some aspects of seismic hazard and risk in the nuclear context, in terms of a very specific application. So some of you may be aware, California actually has 2 nuclear power plants, both of which have been or are being decommissioned. So there's that. This one is the San Onofre station, which is down somewhere between San Diego and Los Angeles. There's 3 units actually. Units 2 and 3 were commissioned in the 80s and are in the process of being decommissioned, as I mentioned. These are pressurized water reactors, and some interesting issues arose with this plant, which I'll talk about. But the story doesn't actually start in San Diego. It really starts in Japan in March of 2011. As all of you are probably aware, there was a very large offshore earthquake about 120 kilometers off the coast of northeast Japan in the Tohoku region. And one of the consequences of that event was an extremely large tsunami that devastated the eastern coastline. And along the eastern coast in Fukushima is a nuclear power plant which has several units. One of them is Daiichi, which we'll be talking about here. At that plant, there was basically a 40-foot high tsunami wave that met up with a 20-foot high seawall, clearly 40 beats 20, and the result of that was extensive flooding of the site. And importantly, both for Fukushima Daiichi and for San Onofre, they're emergency diesel generators, which are meant to supply power to the station and to the critical parts of the station in case of there's a loss of offsite power. So if the power grid goes down, the generators kick on and supply power to things like coolant pumps, which keep coolant circulating through the reactor core and prevent overheating until the core can be cooled off by inserting the control rods. But that takes time, and the control rods, once you insert them in the reactor core, it takes days for that to cool down enough to prevent an accident. So after Fukushima, the US NRC, wisely looked at the effects of at the plant in Fukushima and took action here in the US and issued a letter, which is called the Fukushima letter. Sounds a lot better than CFR 50.54F. And one of the recommendations in the Fukushima letter was walk downs of plants. And the walk down is kind of what it sounds like. You spend basically up to 2 weeks, from what I've seen, looking at every aspect of a nuclear plant, kind of top to bottom, and really looking for vulnerabilities associated with the known hazards, not just earthquakes, but tornado missiles, floods, subsidence, anything like that. So for this project, which again started with these walkdowns, here's what happened. As part of these, well, I've already explained the diesel generators. They sit there. There's 4 of them on the plant. They just sit there doing nothing until the power goes out. Power goes out. They start up and provide emergency backup power. They get tested once a week, but other than that, they don't do anything. Now, each of these generators is equipped with a transducer that's mounted to the top. And that transducer is meant to measure vertical vibration. And the transducer is there to trip off the generator in case there's excessive vibration. And the excessive vibration is meant to indicate that the equipment, that the diesel generator may be malfunctioning. So some kind of eccentric loading, maybe there's a loss of blade or something else that renders the diesel generator inoperable, and it gets tripped off before it basically damages itself or other things around it. So that vibration monitor is very much a part of the story. And a question was raised during the walkdowns. A very bright and astute member of the staff looked at that vibration transducer and said, I know that's meant to measure the equipment's vibration, but what if an earthquake happens and that vibration monitor measures the earthquake movement and then trips off the generator because of the earthquake? And the people at the plant said, it's pretty interesting question. And we're not really sure what the answer is. So they needed consulting expertise. And so Exponent was engaged to basically answer some questions for them. So the retention's like this: determine if an earthquake had occurred in the past, forgetting about the present, because the first thing they did was they stripped off all those vibration monitors and set them aside. So that took care of the risk in a certain sense. But in the nuclear industry, there's a reporting system where you need to report to the NRC anytime you're out of or in violation or in non-compliance, let's say, with the licensing basis. And so the question was, if an earthquake had occurred in the past, would the diesel generators have shut off? And so if yes, that would be an issue for the plant because they would face some retroactive fines and possible downtime to do what's called a red finding, which I won't get into because this is being recorded. And if no, then really there's no real issue to report. And so that's the question, and then yes or no is those are the outcomes from those 2 answers. And so we proposed a simulation to look into this. First is we had to model the actual transducer itself, the vibration monitor, which turns out was fairly straightforward, as you'll see. Also had to model the building structure and the underlying soil. Interesting aspect of that is too that I'll get into, and then develop a set of ground motions that would be consistent with the hazard at the site, so that we could simulate design basis shaking and see the effects of that shaking on the vibration monitor. And then also we need to model the trip circuitry, because remember, this is a control system where the vibration monitor spits out a voltage based on the movement, and then that voltage then goes to a signaling conditioner, which then goes to a relay, which makes a yes or no decision whether to shut the generator off or not. And so that's an electrical engineering issue. So this project was kind of interesting in the sense that we had to leverage several disciplines within Exponent to attack it and to really ask the right questions first, and then to pursue an answer or a solution. And so obviously, building the structures group, that's me in my practice. We also had thermal sciences folk and electrical engineering folk who helped with the circuitry aspect, which I'll talk about. All right, so this is one of these generators. There's 4 of them in the plant, and on the top sits this vibration probe. And if we zoom in, it's a velocity sensor, which basically measures vertical velocity only. And it's mounted to the top of the generator. So this is kind of a PowerPoint style rendition of what this looks like in section. Generator is mounted to the floor slab of the generator building, and then velocity sensor is up here on the top on this rigid crossbar. Now the velocity sensor itself is a very simple device. It measures, it consists of a coil around a mass, and that coil then passes vertically or moves vertically and passes through a magnet. As you probably remember from physics class, as a coil moves through a magnet, it generates a voltage due to Faraday's law, and that voltage is actually proportional to the velocity of the coil. And so it's a spring and a mass and a damper. So you couldn't invent a kind of a more idealized system to model for structural engineering purposes. The only complication is that there's also housing. So there's this casing is obviously not infinitely large. So with enough movement, the mass about which the coil is wrapped may impact the casing. So we had to look at that too. So that's where motion turns into voltage. That's that system. And then we had to consider potential nonlinear response in the case of impact. All right, so the sequence of events is this. The earthquake occurs. The earthquake obviously has 3 directions of shaking. It's not just vertical, but the vertical motion is the one that we're interested in because that's what the vibration monitor is measuring. So motion basically propagates up through the generator into the transducer. Transducer spits out a voltage as a result of that motion. That voltage then goes to a vibration monitor, which then sends a signal to what's called an agostat relay, which takes that signal and then turns that signal into a binary yes/no output. Either trip the generator off, so shut it off, or don't shut it off. And this is a problem clearly because shutting the generator off would then limit the amount of power that was available to the cooling systems. So as an analysis problem, it's take the vertical ground motion and the output is the voltage as a function of time. And so the approach is to develop ground motions, inputs to represent the shaking at the site and through the soil and through the structure. And part of that is, and then a suitable numerical model for both the structure and the soil and the sensor. All right, so the ground motion inputs, I did this using a pretty straightforward approach. Basically take 3 criteria that are pretty commonly applied in ground motion selection and scaling. Define the magnitude of the inputs needed to be greater than 5.5. The source to site distance between 5 and 15 kilometers, and then the soil shear wave velocity needed between about 200 and 400 meters per second. So magnitude, distance, and soil type are kind of the 3 broad characteristics that we look for when we're selecting ground motions. And so I came with a set of 16 that fit within this category that I thought would be representative shaking at the site. And these are the 3 criteria that I mentioned. So take the ensemble of ground motions, scale them such that the median is consistent with the design basis shaking at the site. And by the way, design basis shaking for nuclear facilities, and this one in particular, is 1 times 10 to the minus 4, or a 1 in 10,000 year event. All right, so we had to model the response of the generator. And this is interesting because, as you know, we have very sophisticated tools at our disposal for doing things like soil structure interaction, nonlinear response history analysis of structural elements. And really the question was not about what can we do today. The question was about a potential NRC violation. And so you really needed to analyze this the way the engineers would have analyzed it during the design phase. And so we had to basically go back to the calculations from the 70s and recreate a stick model, which is basically masses connected by sticks, which represent the stiffness of the building and the various appurtenances of the building. And then the soils were modeled using rotational and translational springs at the base. And these are frequency dependent springs. So there was basically an impedance matrix that defined, what the soils, I guess, what the soil structure interaction would be. But it's a fairly crude or kind of classical method of analysis we wouldn't probably adopt today. But again, the question is not what we would do today, it's what we have done consistent with the licensing basis. And the licensing basis was based on analysis done in the 70s. So we put together this model, and the idea is you apply the free field motions here at the base, and those propagate through the soil, and then through the structure and into one of the 4 diesel locations. And so we'd record the output, for example, here. And that's the output that is then goes into the velocity sensor and results in voltage. So we had a model of the velocity sensor. We asked them to send us some so that we could characterize these things. And the first thing they did was they sent us a sensor that had been completely dismantled. And we had to explain, no, we need one that's actually functioning. It needs to work because we need to do some testing. And one important aspect of the sensors is this idea of impact. And from the specifications, there was about 100 mil peak-to-peak travel that was permissible before impact would happen. But we needed to verify that experimentally. And so the transfer function for these sensors is actually fairly classical. So given an input velocity, which is just a harmonic, like what I'm showing here, there's an output, which is the same harmonic, but with an amplitude that is frequency dependent. And this is your transfer function. And so we need to characterize that transfer function over a broad frequency range, because this is how we're going to go from velocity to voltage. And really, we only had data from the manufacturer in the high frequency range, which is where the sensor was meant to operate, but we did not have data in the lower frequency range, which is where the earthquake excitation was expected. In terms of sensor testing, we took a sensor, we went to our extraordinarily small scale shake table in Phoenix. We have a laboratory in Phoenix where we, aside from having a 2-mile long test track, which is where we run cars into each other and smash them up and collect useful data that way. We also have a very, very small shake table, but it was just the right size for these little tiny sensors. So we ran some tests, mounted the sensor to the table, and ran harmonic inputs at various frequencies and recorded the response. And we confirmed for low levels of velocity input that in fact the frequency response function was essentially represented by a linear system or a classic linear system. But when we started looking at different amplitudes of input, we found that as the velocity amplitude got higher, say going from 1 inch per second up to 6, we would see evidence of impact of the coil with the casing. And then at higher amplitudes, of course, you would expect impact as well, more pronounced. And so that basically kind of informed the need for a time domain model. Because if there had been no impact, everything's linear, we could have actually conducted a frequency domain analysis all the way from ground motion input to velocity output. But we were unable to do that because of the impact problem. So complicated things a little bit, but we were able to, in OpenSeas, come up with a fairly straightforward model that would capture both the vibration characteristics of the sensor and the impact behavior. So this plot is showing the simulated voltage output over time, let's say, of a harmonic test, which is the model shown in black, and then the experimental result is shown in blue. We were able to get fairly good agreement within OpenSeas for the voltage response. So then finally, we had to actually test this thing. And that involved in our lab in Menlo Park now, we used basically an oscilloscope to take the OpenSeas output, which is a voltage, and actually physically send that voltage into this vibration monitor, which is, again, is from the plant. They yanked one right off the rack and mailed it to us. And so the way this works, and maybe I'll show you here, is we have the voltage goes into the sensor. And really what's happening here is that there's a capacitor, which is what this blue line is, basically the charge that builds up in this capacitor. And so the longer the duration or the higher the amplitude of shaking is, this charge in the capacitor will build up. And once it reaches a threshold, which the threshold is set within the control, within the vibration monitor, and you see that threshold, basically a trigger goes on. So it goes from 0 to 1. And if that trigger duration lasts for greater than 5 seconds, that's what defines a trip. And I asked them why 5 seconds, and they said, oh, because that relay was dialed to the number 5. And I said, any particular reason? I think we just turned it to the maximum allowable value. I said, okay, that's okay. It's good to know. So So this defines our whole problem now. We run our earthquakes through the soil structure sensor system. We spit out a voltage. The voltage then builds up charge in a capacitor. And if this is longer than 5 seconds, trip off the generator. So we did our simulations for all 16 ground motions. And for the 3 types of sensors that we had, remember there's actually 4 generators, but one of the sensors they sent to us was destroyed. So we had kind of 3 shots at this. So for all 3 sensor types, we ran our simulations. What we found was that there was only 3 instances or 3 realizations, let's say, of design basis shaking where we would get a trigger. And in no cases did that trigger signal exceed the 5-second threshold. So in that way, we were able to conclude that design-based earthquake shaking would not have triggered a shutdown of the generators. So it's a fairly interesting problem in that it relates to seismic risk in a very fundamental way, just because loss of power, loss of emergency power can result in basically core melt and significant hazard to the human population around the plant. But it also involved kind of a weird handshake of a number of different disciplines in engineering, and so it was a unique problem. But I think one fundamental aspect of the problem is that it shows how really bizarre accident pathways can be present that you'd have to be extremely inventive to recognize them. And that's part of earthquake risk analysis, I think, broadly, is that you have to have a fairly fertile imagination in terms of how things might fail and what the consequences of those failure might be. Because missing one of those pathways really means that you're not seeing a source of risk. And to measure risk and to mitigate it, you really have to kind of know what the risks are in the first place. It's kind of an obvious thing to say, but it's actually kind of difficult in practice to define those pathways. So I think a lesson is be creative and think of all the ways something might go wrong. It's not you being pessimistic; it's just being realistic and being a good analyst. Okay, I want to talk a little bit about post-earthquake reconnaissance, in part because it is, I think, something fundamental to EERI's mission, but it's also a place where lessons are learned every single time. I remember one of my advisor, Professor Steve Mahan, who's unfortunately passed on. He likened earthquake engineering to tort law, where or common law, where a law doesn't exist until a judicial body basically passes a ruling, and now that becomes a law. And the more rulings there are, the more laws there are. And so every time we learn something from an earthquake, we then kind of create a law that we can follow, or that we can a rule to live by, to kind of improve the performance of our environment in the next earthquake. So with that backdrop or in that context, I want to tell you about my trip to New Zealand, which is, by the way, a beautiful country. And I would love to go back at a time that was not a national disaster. There's a city, Christchurch, which is in the Southern Island. As I'm sure you know, New Zealand as a country is highly seismically active, and the whole country more or less is subject to some form of seismic hazard. Now, an interesting, I guess, aspect of the New Zealand Christchurch earthquake in February of 2011 is that it was technically categorized as an aftershock of an event that occurred in September of 2010. The main shock in 2010 caused fairly little damage in Christchurch, whereas the aftershock in February of 11 caused significant damage to the central business district. And part of that was due to the magnitude 6.3, which is significant, smaller than the main shock, which I think was 7.1. But it was 9 kilometers, so very close to the central business district, which, as you'll see, is endowed with a number of unreinforced masonry buildings and non-ductile concrete buildings. But it was also very shallow. The depth of the event was 5 kilometers, which is, by earthquake standards, is extraordinarily shallow. And the effects of that are fairly dramatic. I think, I won't say people, but I sometimes forget that the source to site distance is 3-dimensional. It's not just the distance in plan or horizontally, but it's also the distance vertically. And so the depth is a huge contributor to potential shaking and seismic intensity. So this it was a not atypical scene in the central business district of Christchurch after this earthquake. There was a lot of damage to unreinforced masonry facades, exterior walls, parapets, and certainly concrete buildings, especially those that were relatively non-ductile in terms of having wide tie spacings in the columns and in the plastic hinge regions of the beams for moment frame buildings. And a lot of the damage was to modern concrete construction. So these are buildings that were built, relatively recently relative to the earthquake's occurrence, built to modern codes, and there was the kind of damage you would expect in a large earthquake. There was spalling in the in the boundary region of the shear walls. There was spalling in the plastic hinge region of the beams. There was buckling of rebar in between the horizontal ties. And this is expected, right? This is a large earthquake, and as we'll see, it was probably close to or even in excess of the design basis earthquake for the region. In a large earthquake in an urban area, you expect there to be significant damage, and potentially buildings need to be demolished following a design level earthquake. And from what I saw and from the people I talked to, and even within the government and just homeowners that I encountered or business owners, I don't think this was an appreciated fact of code-based seismic design. I don't know that it was entirely understood or appreciated that designing a building today, according to the modern codes, the potential outcome would be that the building would be entirely unusable after an earthquake and would need to be torn down. I think that's important for the public to recognize that and to appreciate that, and if needed, to take action to improve codes or enable, I guess, stakeholders and engineers to do better if they so desire. So that was, I think, a good lesson from the Christchurch earthquake, is that acceptable levels of damage may not be actually acceptable to the public once they find out about it. Another thing we saw, which I thought was fascinating, was that in certain areas, like even along a block, a lot of the construction along that block, say, predated a major earthquake in New Zealand from 1931, the Napier earthquake. And the types of damage there was fairly substantial relative to, say, a block away or 2 blocks away, where a lot of the buildings were post Napier, so built after the earthquake. And the lessons learned were fairly dramatic. There was the walls were much better tied into the diaphragms. There was better confinement in the concrete. Better reinforcement of the masonry walls. The difference was fairly stark and easy to appreciate. So talking about the actual intensity of shaking itself, there were showing the spectra, you can clearly see. So in red here, this is the main shock from the 7.1 earthquake in September of 2010. You can see that basically across almost all period ranges in downtown, this is in central Christchurch, it's actually near the hospital. The aftershock in February was significantly larger than the main shock. And in fact, it exceeded the 475-year design basis earthquake in the area. So, and the fact that, and I don't actually know what the numbers are to this day, but at one point recently, it had been estimated that about 50% of the central business district was or needed to be demolished. And this is not an unexpected outcome of a design level earthquake, is that buildings may not be occupiable, or it may not be financially feasible to repair them and rehabilitate them before being used again. So this is what happens when you have design level shaking in an urban area. So, and our codes and codes worldwide are really kind of moving in a risk-informed or towards a risk-informed framework, to the extent that they haven't completely. But really, the idea of seismic risk is somewhat, well, it's a straightforward idea with many complications. But the idea is that the risk of failure for a component or for an asset is basically the exposure times the hazard. So likelihood of an earthquake of some intensity occurring times the damage state or probability of failure of that structure given that level of seismic input. And I think importantly, the red, the hazard, is not something that you or I can do much about, right? The hazard at the site is dictated by things that are beyond our control. So this part of the equation is somewhat provided, The exposure, however, the way structures respond to earthquakes is largely in our control, and we can do a lot to affect the likelihood of failure given seismic input. And that's generally, represented by some type of fragility function. And there's many different types of fragility functions or fragility curves, but they all basically define what the probability of failure of a system given a level of input. And that also has some uncertainty about it as well, right? Just because we say something has a 50% likelihood of collapse, well, that can't be deterministic, because if you run 10 experiments, you'll probably get 10 different answers. But this is the framework. This is how we design things in the modern era, whether explicitly or implicitly, as we're trying to target some acceptable or palatable probability of failure. And really, that's where I think engineering and ingenuity and innovation really come in, is in trying to reduce that probability of failure, or moving that fragility function, because that's, again, the thing that we can do to improve earthquake performance, is change that fragility to something more attractive. And the way those are done is with strategies like seismic isolation, which is something I've been kind of working on for the last 25 years, more or less. Adding passive damping or some supplemental damping devices that kind of absorb energy in kind of distinct locations and free up the rest of the structure from absorbing that energy, which might cause damage. And then also self-centering systems, which kind of mitigate against post-earthquake residual drift. And those residual drifts are the demands that often characterize the cost of repairs and the likelihood of needing to be demolished. So these are all technologies that have seen kind of widespread development in the research and in industry as well. We've implemented isolation, damping, and self-centering systems in buildings and bridges worldwide. But that's the fundamental reason that they're attractive to us in this risk-informed framework, is that we're changing that probability of failure. So seismic isolation, I won't go into the theory behind it, because I think it's somewhat well known, but the idea simply is that whereas a fixed base building, when being shaken by an earthquake, the displacement demand tends to be distributed throughout the structure itself. For a base isolated building, you're really focusing that demand in a specific layer, which has been detailed explicitly to absorb that type of deformation. So isolation systems are very good at absorbing large displacements. Traditional building structural systems are not as good at absorbing that same level of deformation without extensive damage and potentially collapse. So videos are often more instructive than photos, and we can kind of see what the effect of isolating a structure is. We're reducing not only the amplitude of the deformation in the structure itself, but we're also affecting the frequency content and ultimately the acceleration input at the various floor levels. So isolation is really one of the few technologies that's available where you can reduce both drifts and acceleration simultaneously. With traditional structural design, if you want to reduce displacements, you add stiffness and strength, and that tends to drive up acceleration input. You can make it more flexible to reduce acceleration, but then you're paying the price with increased deformation demands, which cause structural damage. We've also looked at isolation for taller buildings. I used to be of the opinion that it didn't make sense to isolate a tall building because it was already flexible. And why would you add a flexible layer to a flexible building? You're not really achieving that kind of period separation effect that we're often going for. But what I found in some of my research and what I've seen in some published literature is that the flexible layer for the tall building it's not elongating the period and changing the frequency content, but what it is doing is providing a compliant layer at the base, which is going to absorb deformation that otherwise would have gone into this tall building. And so it is effective at reducing drifts. And really the only challenge really is for a tall building is dealing with some of the overturning effects and the tensile demands on the exterior bearings, but we have ways of handling that too. And then I'd be remiss if I came to Reno and didn't show a video of Professor Kerry Ryan's amazingly successful tests that were done at the E-Defense facility in Miki City outside of Kobe. This is an experiment that was done on a 4-story seismic isolated, 5-story seismic isolated steel building on a variety of different bearings. This was a test done on triple friction pendulum isolators. And what you'll see from this video, and maybe I'll run it again in a second, but you can see the way the isolator behaves is really meant to, mitigate demands in the structure. But it's really, if you look at the contents, is really where some of the benefits can be seen. So really the ground is kind of moving underneath the building. The building really largely stays put. But the contents inside relative to a conventional structure are largely kind of undamaged and usable. Now, of course, I didn't show the one with the vertical acceleration, and Professor Ryan can give you a detailed explanation of what the effects are there. But these are damage to ceiling systems is important, and it's a non-structural component that needs to be dealt with appropriately. But the point is, this video I think really illustrates a lot of the benefits of implementing a technology like this. And it was frankly just a really cool test, and I was happy to be involved with it. So thanks, Gary. All right. So really what we're doing, in my view, is in trying to mitigate seismic failure or the probability of failure. We can't do anything with the hazard curves, but what we're doing is we're taking the fragility function of our components, and we're not only moving that fragility function over to the right, which is to say, for a given input, there's a lower probability of failure, right? But we're also improving the uncertainty or decreasing the uncertainty of the response. And with isolation and damping and certain self-centering hardware, these are devices that are actually tested in a laboratory and are characterized before they go into a building, right? We can't and will never test every shear wall before we build it, or every beam column joint before it's constructed on site. But we can and do test isolators and dampers completely before they show up and get put into a building. So we're I think we're doing two things in the risk framework. We're increasing the capacity, but we're also limiting the uncertainty around that estimate. And these are things we need to be thinking about as we move forward and become more comfortable with this idea of characterizing uncertainty explicitly in our design methods, and maybe not relying as much on prescriptive code provisions where these ideas are kind of opaque and are kind of in the background. All right, one of the last things I want to talk about is one of my favorite earthquake related projects, which of course happened in Virginia. Where else would it have happened? So you may remember, depending on where you lived, you may have been affected by the Great Virginia earthquake of 2011, which happened in Mineral. And this was something from a social media site by Perez Hilton, who I don't actually know who that is, but I think he must be an influencer of some sort, or was at the time. In any case, this earthquake attracted a significant amount of interest and kind of excitement in the United States at the time. I think because largely no one thought earthquakes happened in Virginia. But no one at the USGS was surprised by this, because there is a well-known series of faults in the region, and it has produced fairly large magnitude earthquakes over the years. So important thing to know about earthquakes in the US is that East Coast earthquakes are not the same as those in the West. And a lot of that's because of the geology. Basically, earthquake waves travel in the East Coast because of the kind of the age of the underlying rock, and kind of the lack of significant numbers of fractures due to very regular seismic activity. The waves tend to travel very long distances without attenuating, and so the consequence of that is, for a particular event in the East Coast, there's a lot more exposure of the built environment to that shaking, and more potential for damage, even in places that are far away. I grew up in California, spent most of all my childhood and a good portion of my adult life there. It's kind of well known that earthquakes that happen in Los Angeles would never be felt in San Francisco, and vice versa. It was just, we wouldn't perceive an earthquake that was 500-600 kilometers away. Not the case in the East Coast. Earthquakes that happen in Virginia, for example, can and are felt up in the Northeast, down in the South, in the Midwest. I'm actually going to posit that the person here in Texas did not feel that earthquake. I think that a truck might have driven by their home around the same time. It's just my speculation. But the fact remains is that it's not unheard of for an earthquake to cause damage, fairly far away, even a moderate event. So again, in that context, I will tell you about one of my favorite projects, and that is alleged earthquake damage to a series of swimming pools at a summer camp in New Jersey. Anytime I've given an opportunity to go visit Central New Jersey, I'm always going to take it. So this was such an opportunity. So this is probably about 2 weeks, maybe like a month into my job at Exponent. I just moved from Japan in March, I guess. I started in April of 2012. The Mineral, Virginia earthquake happened in August of 2011. And basically what happened was the management of the summer camp, they basically vacate at the end of the summer when the campers are gone. they leave for the winter, and then they come back in the spring to kind of get things restarted for the next summer. So just to get you oriented on site from a satellite view, there's 3 swimming pools on site. And what they had said was, you know, hey, listen, when we came back in April, we walked down, we were going to do our cleanup and get things ready for the summer, and we found all this cracking and spalling, and I don't think they use those words, but they, you know, a lot of damage to the various concrete elements of the swimming pool. And so I got a call from an insurance adjuster. So the way this works, right, is that the management or the ownership of the summer camp has an insurance policy for various different kinds of risks and hazards. They one of them is earthquakes. They call up the insurance adjuster, they file a claim, and they say, hey, or the claims manager, and they say, hey, I think I've got earthquake damage. I want to submit a claim under my policy. The adjuster goes out there, looks at it, and says, well, I don't know if this is earthquake related, to be honest. I wonder if there's someone who can help me out. And so they contact experts like us at Exponent and other firms as well. And we conduct an investigation on behalf of the insurance carrier to look at causation of the damage. And so I got in a car, I went down to Jersey, and you know, brought my tape measure and various different types of measuring equipment. Very excited to see real life earthquake damage on the East Coast. So I showed up, and this is kind of what I saw. I saw a lot of, you know, spalling and cracking of the concrete hardscape near the coping of the pool. So I took a picture of it. I saw cracking around the railing, the anchorages of the railing to the pool deck. So I took a picture of that. Saw a lot of evidence of like scaling and, you know, cracking and basically deterioration of the surface of the pool decks. And so I took pictures of all of it. And, you know, my first impression was this doesn't seem like an earthquake damage mechanism to me, especially not one of, you know, where there was fairly low intensity of shaking. But, you know, I'm going to conduct my investigation as I should. And so I went back and looked at the USGS shake maps. So the shake map for the region from the Virginia earthquake, this shows the modified Mercalli intensity, which is a qualitative measurement of earthquake shaking at a particular site. So this kind of incorporates, you know, side effects and distance and everything else into it. And so these are estimates of intensity of shaking all around the East Coast. And obviously the lighter colors, the kind of the cooler colors, the blues, the aquamarines, the greens, those are kind of low levels of intensity that really aren't expected to cause observable damage. Maybe once you get into the greens and the yellow, you start to get some non-structural damage, perhaps. Well, in this part of New Jersey, the color scheme was very much in the very cool area. It was, you know, 3, maybe 4 on an MMI scale, which you wouldn't predict or expect damage to slab on grades or other kinds of pool features. But all right, that's one piece of important data to consider. There's also a strong motion recording station at Drexel University that's in Philadelphia. So I went and pulled that data. And what that data told me is that the peak ground acceleration at the site, in Drexel, which is actually closer to this earthquake source than the summer camp, the shaking there was 0.007 G in the vertical direction. So this is 0.7% G, right? So that would be like me accidentally probably running into Carrie's desk on my way, you know, into her office, and that's the level of vibration that would probably be experienced. Again, another data point indicating that probably this damage was either pre-existing or it was due to some other phenomenon than earthquake shaking. But finally, this is fairly typical. You can't do an investigation without going to the internet in general, and in particular, things like social media sites, other places where photos are widely available. This is an extraordinary source of important evidence that we can consider in our analysis. So this website for the summer camp, again, it runs from June to August. So the camp ceased operation on August 19th. 4 days later, August 23rd, the earthquake occurred. So what this means is that every single picture on this site, and there are thousands of them, every single one of them was from before the earthquake. So they all predated the event. So any conditions that were present in these photos would not have been earthquake related. So sure enough, break open the pictures, and that cracking and that spalling that looks really familiar. And sure enough, it was the exact same location, same type, and kind of size and kind of amount of damage, let's say, as what I observed, and that was present in the summer prior to the earthquake. Same thing with some of the scaling of the pool deck. Very much all the cracking was there, and that cracking again was still there once I went out there. And that anchorage of the railing to the pool deck, looks familiar because it's the exact same place and the exact same pattern. So it was fairly straightforward to conclude at the end of it that that the earthquake, that the cracking and the distress of the pools was basically pre-existing condition and was unrelated to the occurrence of an earthquake. So the point of that story is that when, and this is true, not just, pool decks are fairly infrequent source of earthquake reconnaissance or investigation, but even for massive residential and commercial projects, when you're out looking at damage and whether it was caused by an earthquake, you really have to think about not only is this a likely mechanism for earthquake damage. I mean, if you see shingles missing from the roof and someone says that's earthquake related, well, shingles are extraordinarily light and it's probably not. We have to think about mechanisms and then also think about what the data says the intensity of shaking would have been. And that's one important part of it, using kind of technical sources of information. But also you got to go to the internet and look at photos. And I can't tell you how many times I've used Twitter and Google Street View to come to a view as to what kind of damage was due to what source, just because people are obsessed with taking photos these days, and they're even more obsessed with posting them all to the internet. And people like me who are trying to figure out what somebody looked at a particular place and time love those kind of photographic evidence, and they leave all the metadata in there, so you know exactly what date and time it was taken. So it's a brave new world we're in, and just happy to be in it. All right, so by my clock, I have 5 minutes left. That might not be by the moderator's clock, but I only have a little bit more to say before we wrap up. And I want to talk about a recent extension of seismic risk assessment and the ideas that are embedded in there. And I refer to this at the beginning. This really deals with wildfires. As everyone is aware, wildfires are a major problem for us as a society. They happen from natural events, from man-made events. And as some recent wildfires in California have taught us, they can be the result of utility assets. So electrical assets that, through wind or other phenomenon may ignite a fire that may then turn into wildfire. And the human toll is kind of staggering, honestly. Setting aside the economic damage, is just the amount of human suffering that's resulted from these wildfires is really sometimes hard to fathom. And so it's a hugely important priority for utilities nationwide, really, to kind of get a handle on what they can do to minimize the risk of wildfire ignition. And that really starts with understanding the risk. And so we at Exponent, and I'm sure there's others as well that are engaged in this, but we are working with various utilities in California and helping them develop these kind of risk-based utility asset management programs, which is really asking these questions. How can we use the limited resources of the utility to best manage wildfire risk, as well as other risks, but talking about wildfires, and how can they be intelligently allocated to kind of address maybe the most vulnerable assets? And how do you determine if something's vulnerable? Well, you develop a risk-based framework of evaluation, and you can basically back calculate where the risk originates from, and then kind of mitigate by going to the most, where you can get the most bang for your buck. So really what we're doing is in part developing wind fragility functions for towers subjected to wind. And really corrosion of these towers is a major factor in how vulnerable they are to damage due to wind. And a lot of the driving forces for corrosion are things like proximity to the ocean, where the chlorides are, proximity to industrial areas where we might see sulfites, or sulfur dioxide, and then what kind of temperature and humidity environment these assets are in. So we can develop fragilities based on these kind of metrics. And then what we really need to do then is just like what I explained with, the entire peer framework, or the earthquake risk framework, is really about convolving the hazard with the fragility. And again, we can characterize the wind hazards. We know the likelihood of an asset, like a utility tower, being exposed to a certain wind speed. And then we can characterize the probability of failure of that tower or a component. It doesn't have to be just the tower, it could be the conductors or some other element. And we can characterize the likelihood of failure given a wind speed. And what we're doing in a lot of these assessments is we're using a Bayesian framework to basically take survival data of various towers to known wind events, and then updating our fragilities based on the fact that, well, if they survived a 70-mile-an-hour wind and there's no observed damage, then that knowledge should be factored into our prediction of future failures. And that's most easily done using basically Bayesian updating, where we form a prior distribution for the fragilities, update that to form a posterior distribution, having observed survival data. And then we measure the risk by kind of lumping things qualitatively into these various bins, where basically taking into account the frequency of a certain wind demand, and then the consequence of failure, and then kind of prioritizing which assets to look into, kind of based on this sort of matrix. And then we kind of rank the various towers, let's say on a circuit, by most vulnerable and most likely to be subjected to a particular input. And then based on this ranking system, we can go and kind of de-energize until they can be upgraded. We can de-energize some of the assets that are considered to be weak or vulnerable until repairs can be done. And that de-energization will minimize the risk of wildfire ignition on that circuit. So that is my set of prepared remarks. So I thank you very much for your attention. It's always a pleasure to talk to groups like this. Of course, I'm staring at a screen hoping you all are nodding and agreeing with me, but I really have no idea. But it is really my pleasure to communicate some of these ideas, to talk about them, to share some of my thoughts and experiences. It has been an adventure, as you've probably seen, and that's really a kind of a subset of the many stories that are out there, kind of about lessons learned and how we can maybe move forward in the area of earthquake risk mitigation and assessment. So, and thank you to EERI for funding my visit, as it were. I'd much prefer to be there in person, but that'll have to wait. All right, so I will be happy to take questions or have a follow-up discussion at this point. So thank you again.
Thank you much. Thank you so much, Dr. Morgan. This is Mohammed. I'm sorry I missed you. To introduce you earlier, I just had to attend to some matter here. But as we have announced to our students, we still have a full 1 hour, to benefit from Dr. Morgan's expertise and get some clear advice. So if you have questions related to the presentation, that's a good time to ask. Or even if you have, questions beyond the presentation, I'm sure Dr. Morgan will be happy to share some insights with us. So we have a lot of time. We understand that the capstone students might need to leave, so feel free to do so. And for our graduate students, please take advantage of this. And thanks, Troy, for the very informative presentation.
Thank you. Don't ask all at once, please.
Okay, all right. Well, first it looks like Matthew Offspun asked a question in the chat. Matthew, do you want to say that yourself, or is he still here? Or did he leave?
Sure, I can say it myself. I was just curious, you were referencing the damage in New Zealand. Some of the neighborhoods were predated to the 1931 event, and that event seemed to be pretty significant. Are any of those predated neighborhoods that are still exist, are they analyzed for risk from damage from that original earthquake in 1931?
Oh, you mean like if a infrastructure of a building were weakened from that event, and what the effect would be on? Yeah, no, that's an interesting question. Typically there's periodic inspections of buildings, bridges, and other kind of important infrastructure, and those inspections would hopefully reveal any damage, and then that damage could be repaired, either epoxy injection or other ways of bringing the strength back up to its full value. That said, so I don't know about the 1931 event, but I did read a paper recently, actually, I think it was an Earthquake Spectra, where I think a group of New Zealand researchers actually addressed this question of kind of weakening of building systems due to earthquakes and the susceptibility of failure, say due to aftershocks or due to a future earthquake. And so it's an area of research that I think is really fascinating. And that's about as much as I can probably say on it from my own perspective. That's a long way of saying I don't know, isn't it?
Thank you.
Actually, I have a colleague that never says I don't know. He says, I don't have a specific answer to your question, which I think is brilliant.
Well, hopefully you'll have a specific answer to the next one. Maha, if you would like to ask your question.
Yes. Thank you, Morgan, thank you, Troy, Dr. Morgan, for the presentation. It was really, really cool. And I think it was also educational. I found the story of the cracks near the swimming pool to be really interesting. And I was wondering, how common is it that entities or insurance companies would mix up or think that something is caused by an earthquake damage and turns out being caused by something else?
Right. So it's it's a good question, and I'm actually going to answer it and then make some comments about that, I think that general topic. First of all, the insurance companies often, if they are not certain of the causation of something, they will retain an expert, because the last thing they want to do is to come to a conclusion that would result in lack of insurance coverage, and then to have someone bring suit against them for bad faith or whatever, and then it to be revealed that the insurance adjuster really wasn't qualified to have made that determination. And so they're fairly, I think, kind of willing to engage experts to look at these causation mechanisms. And the insurance agency or the adjuster never said he thought it was earthquake damage or not. He just said, I'm not really qualified to make that determination, but I think you are. Can you please go out and write a report? And then I write the report and I send it to the insurance company, and I have no idea what happens after that, which is a good thing. I don't care about the coverage. I haven't read the insurance policy. I don't care what the outcome is for the insured. I just do my engineering analysis and move on. What I wanted to say about your question, though, because it brings up an interesting point, is, well, are these, is the insured trying to pull one over on the insurance company? Are they seeing this and going, I know this isn't earthquake related, but listen, I got a policy. Let's take our best shot and see what happens. In my experience, and I've done this a lot with both earthquake and probably more of hurricane damage, because I was after Hurricane Sandy, and I talked to the capstone class about a pretty major project after Hurricane Sandy. I believe firmly that it is a psychological issue of detecting damage and attributing it to a cause. If you walk around your house or your office right now, if you look around, you will find a crack. I can tell you. Okay, if you don't have to look that hard, you'll find one, and you wouldn't think twice about it, or you might even see it. But if someone told you, hey, there was an explosion next door, you should go look for any damage, you're going to find it, right? Because it was always there. You just never knew to look for it. And I really do believe, because I've talked to these people on site, I've listened to them. These are, these are honest folks who are just really worried about their home. They're really scared because they just went through a disaster, and they think that they're seeing damage attributable to that cause. And I get it. But I think it's a human emotion. It's a matter of psychology, and it's not a matter of sort of nefarious intent or some attempt at fraud. But I think it's important to know that, because I think we have to be respectful of that, especially and during earthquake reconnaissance. You have to realize that these people have been through perhaps the most significant and traumatic event of their lives, and this is their home, which most people's wealth is tied to, right? So there's a lot of emotions that are tied up there. That was, by the way, a total diversion from your original question, but I hope I answered your question in addition to that.
Yeah, you did. Thank you.
Okay.
No, it's really interesting. Thank you very much.
Mm-hmm.
All right. I'd like to ask the next question, but before we do, we're losing people. And for our report to EERI about how this went later, we'd like to get a picture. So before I ask my question, can I ask everyone to turn on their video real fast and wave at the camera?
Like that? You got to give us a countdown, by the way. So I don't.
Okay, I'll give you a countdown once we get a couple more. Okay. Everyone smile on 3. 1, oops, wrong button. 1, 2, 3.
We done?
Okay, thank you all.
Right.
Okay. And you can all go back to turning off your videos now. Okay, so my question is, when you're doing, when you're looking at the Fukushima disaster, do you look at any of the other nearby power plants that didn't experience meltdown as well, when you're making decisions for some of our local plants?
Well, yeah, and actually I wrote a proposal at one point, and I think this work got done, but just not by me. But it was to go and look at the other plants in Japan that were, and so the Onagawa nuclear plant is actually very close to the seismic source. It was about 120 kilometers, because it was basically very close. It was on the coast, which most plants are for cooling reasons, and it was pretty close to the source of the earthquake. And what we were interested in doing is going to the Onagawa plant and looking at all the survival data from all the pieces of equipment that weren't damaged, right? Mm-hmm. And then and then updating the fragility functions using that same Bayesian framework like I talked about for the electrical assets, and then coming up with kind of basically improved estimates of seismic risk for plants. Because a lot of these anchorage details and a lot of kind of the ways that these nuclear plants are designed are fairly standardized worldwide. And in fact, a lot of plants are standardized because they actually do follow what's called a standard plant. There's one nuclear plant that's being designed for like a generic site, and then they deploy that plant to various sites and then update the design or modify the design to account for local effects. But the fact that it's so standardized, it's a great opportunity to go and basically look at things that did not fail, or that did, if that's the case, but there's a lot more examples of things that didn't fail. Onagawa plant was, as far as I know, was essentially undamaged and was in operation shortly after the event. So that's the kind of thing we do. We do go to other nuclear plants that have experienced strong shaking for, is to gain information and update some of our estimates of risk based on things that basically didn't go wrong. Yeah, so that's probably the extent of it. I mean, all the plants are, by the way, they all have walk downs after a major earthquake, and not even a major one, even a minor one. There's a full, very detailed examination of all the components to confirm that there is no damage.
Okay, thank you very much.
Mhm.
And now Dr. Ryan has a question.
Yeah,
I could ask many.
you can and you will, I'm sure.
I can't dominate the conversation. But, well, thank you very much for your presentation. It was very informative and entertaining, as always. Really appreciate